Okay, everybody. So we are going to extend our understanding of work and energy a little bit in this screencast. Now, the screencast could be a little, it might seem a little confusing. So I want you to look through it, and then we can discuss any issues that we have. But we we want to be able once, by the way, once we get this down, it's actually really easy to solve some physical problems using concepts of work and energy, easier than using Newton's laws. And so that's it's a very powerful way of describing things. Now, we're going to talk today about something called conservative versus non-conservative forces, and I'm going to simplify that in a minute. But basically, uh, if we were to look at the work done by each of these forces, these are all basically non-conservative forces. In fact, the only conservative forces we're going to be looking at are gravity and spring forces in ideal springs. And we'll talk about those later. Today we'll talk about gravity. We won't talk about springs yet. But basically, if we were to look, remember the work energy theorem, if we were to look at the work done by each force, we would take, if this is moving to the right, we would take the component of this force, multiply it by whatever distance it travels, and that would be the work done by the pulling force. The work done by the friction force would be negative because it's the opposite direction as the motion, and it would be this force, the kinetic friction force, times however far you went. And the net work would be the net force times the displacement, or this force minus that force. And we know from the work energy theorem that if you do net work on an object, that amount of net work is equal to the change in kinetic energy of the object. And that's our starting point. Our starting point is the work energy theorem. The net work, total work on an object, is equal to the change in kinetic energy of that object. All right. But what there's a special kind of force called a conservative force. And basically what we can do is we can use these types of forces to create an isolated system in which there's no work done externally on the system if we treat it completely in terms of energy, which we'll talk about in a little bit. But basically, gravity, a conservative force, is a force that the work done by that force is independent of the path you take to go from point A to point B. So it doesn't matter if she goes down this water slide to the bottom and out to here, or she falls straight down. The work done by gravity is really the component downward times the distance, which is just the force of gravity, mg, times the distance, call it y. It doesn't matter if she goes this way or this way. And you can prove this to yourself by, if you had a slope with a certain angle, you'd be able to figure out the work done along the incline, and it'd be the exact same as the work done here. It's independent of path. But friction is an example of a force that is not a conservative force. So if you took a book and you went from A to D, or if you went from A to B to C to D, the amount of work that friction is going to do is going to be 3 times as great going this path than that path. So it depends on the path. Conservative forces are a special type of forces where it just doesn't matter how you get from point A to point B. The amount of work done by the force is the same. Okay? So we're going to use that idea to determine something called potential energy. In this case, we'll talk about gravitational potential energy. Now, you guys have probably discussed potential energy back in ninth grade, and potential energy in general, you can think of it as stored energy. And we'll be more specific about this again later, but potential energy is something that can be turned into kinetic energy. So gravitational potential energy is energy that's stored in the gravitational field of an object. So if I lift something up, because I know if I let it go, I'm going to convert what I did in lifting it up into kinetic energy as it falls. And there are other types of potential energy. There's electrical, there's chemical, nuclear. All those things are, they're stored until you unleash them, and they can turn into kinetic energy. Now, if I'm going to compare it to the work done by gravity. Basically, gravitational potential energy change is basically the opposite of the work that gravity does in making that change. So for example, the work done by gravity as this thing falls is mg times delta y. And mg delta y is mg times y initial minus y final. Delta y is y initial minus y final. And so the work done by gravity is that much. And we're going to define the potential energy as just the negative of that. So as the more positive work is done by gravity, the more potential energy I lose by the same amount. So the work done by gravity is equal to the loss in potential energy. And if you can think about it as if you're up here, you have more potential energy. Gravity does work. As it does work, you increase the kinetic energy and you're losing the potential energy due to gravity that you had. So really the work done by gravity and the gravitational potential energy are sort of flip sides of the same idea. Okay? Now, this is a little, well, let's just do this. I'm doing this because I'm doing it slightly different than the text in the book. I think the way the book presents it is a little confusing. So I'm trying to tighten it up a little bit and get to the main points as best I can. And we'll discuss it just to clarify. But the work energy theorem says the net work equals the change in kinetic energy. But if I have more than one force doing work, I could write it as it's the work done by all the non-conservative forces plus the work done by all the conservative forces. Because in any case, the total work is just a tally up of all the works. And that still equals the change in kinetic energy. That's the work energy theorem. Okay, so since the change in potential energy due to gravity is equal to the negative work done by gravity, we can write that the work done by non-conservative forces basically equals the change in kinetic energy plus the change in potential energy. So basically what we're saying is simply that if there is work done on the system, that work can go into two things. It can go into changing the kinetic energy by speeding it up or slowing it down, or in the case of gravitational potential energy, it can also go into lifting or pushing the object down in terms of gravity. So basically, the work net is equal to the change in kinetic energy. But the work done by non-conservative forces might be the change in kinetic energy plus the change in potential energy, because this right here is really just the work done by the conservative forces, negative. So it really is saying the same thing. So what I'm doing is I'm taking gravity and I'm turning it into an energy term rather than leaving it as a work term. I could do it either way. They both work. No pun intended. Okay. So for example, if I'm pushing something up an incline, I'm doing work let's say I'm speeding it up as I push it up the incline. Therefore, I'm increasing the kinetic energy, but not all the work is going to increasing the kinetic energy. Some is also going to increasing the potential energy. So in that example, I could just look at the work I'm doing is going into those two things, rather than if it was a flat surface, it would all just be going to this one thing. And really all I'm saying is that gravity is also doing work at the same time. And so if I bring this over here and make it the negative sign, then it's really still just equals the total work done equals the change in kinetic energy. But the reason we're doing this is we're saying, well, what if the work done by non-conservative forces is zero in our system? Then we can look at the whole thing in terms of energy. So if the work done by non-conservative forces is zero, then basically what I'm saying is that the total kinetic plus potential energy before something happens equals the total kinetic plus potential energy after it happens. And that is a statement of what's called conservation of mechanical energy. In an isolated system, if there's no work done by non-conservative forces, the sum of the energy remains constant before and after an interaction. So for example, if I have a frictionless bowl and I put a block on the top of the bowl and it slides down and back up again and down and back up again, I can ignore the work done by gravity and put it in the form of the potential energy due to gravity, and then I can say that the total kinetic plus potential energy of the system remains constant. And I'll do an example of that in just a second. Now we could still do it, we can do it in either way, in terms of net work equals change in kinetic energy, or in terms of if I don't have any non-conservative forces, I can just talk about the total energy before equals the total energy after in a conserved system like this. Okay? A quick side note. Gravitational potential energy is really, when we talk about it, we're just talking about a change in potential energy from one point to another point. So basically, we can set our zero level whatever we want. If I'm worried about the book going down to the table, then I can just set the table equal to zero potential energy and the book at a distance y above that height. But if I care about the floor, then I can set 0 to be here, and I have more potential energy relative to the floor than I do to the table. But it doesn't really matter, because all that matters is what is the difference in going from this point to this point to this point, or this point to that point. I just set the difference in potential energy levels to suit where I'm going to end up or go to. Okay? So, conservation of energy. If there are no non-conservative forces during work on the system, then I have energy conservation as expressed by this equation. And so I can throw the ball up horizontally or down. And if I throw them at the same speed, then my total energy is going to be the same in all three cases. It doesn't matter if I threw it upward, sideways, or downward. I know that I had a kinetic energy that was due to my speed, not my velocity, a potential energy that's due to my height. So all three of these throws, if they're thrown at the same speed, have the same total energy, and therefore will have the same total energy at the bottom. And I can write it out in terms of the specifics of each: kinetic energy, potential energy initial, kinetic energy plus potential energy final. And if I want to find, for example, if I don't know the mass, it doesn't really matter if I'm just trying to find, for example, the final velocity. Okay? Now, in this case, they're all with the same initial speed. The first ball is thrown horizontally, some angle below. Rank the speeds as they reach the ground. Think about this for 1 second. 2 seconds. Pause it. All three balls will strike the ground at the same speed. Not at the same time, but they all have the same total energy. They all lose the same exact amount of potential energy, so their kinetic energies must be all identical at the bottom, because the only thing that changed, they all have the same initial kinetic energies and the same initial potential energies. They all have the same final potential energies, so they must all have the same final kinetic energies and therefore the same speeds. Okay? Here, they both start, Bob and Esther start at the top. One starts from the top of a tree limb. Esther starts at the descent down a frictionless slide, which is true about their kinetic energies. Well, they have the same kinetic energy because the loss in potential energy is identical, or you could say that the work done by gravity is identical in both cases because the work done for a conservative force is independent of path. So in terms of energy conservation, they both have the same energy at the top, which is all potential. They both lose the same amount of potential energy, and therefore they have the same kinetic energy at the bottom. Or you could say that gravity does the same work on both of them. You can think of gravity in the form of the work-energy theorem, and the work net is the change in kinetic energy. Okay? So we're going to do some problems using applying conservation of energy. And so basically, you're just going to follow these steps. You're going to identify the beginning point and the end point. You're going to set a y equals 0 point for potential energy. You're going to write down the conservation of energy equation. which is what we just saw above. KE initial plus PE initial equals KE final plus PE final. Find what we're looking for and solve. Okay? So we'll do an example of that. Okay, this, you can't see the top, it's off the screen, sorry. But it basically says a block of mass 2 kilograms is going down a frictionless track at a speed of 10 meters per second. Goes down a 4-meter high incline, and we're going to find the block at the speed of the block at the bottom of the incline. And this is a standard conservation of energy question. And we can do it using work and change in kinetic work energy theorem or conservation of energy. They both work. So if I set y equals 0 at the lowest level, I know my kinetic energy initial plus my potential energy initial equals the final values. And then 1/2 mv squared initial plus mgh is my energy at the beginning equals my energy at the end. I have 0 potential energy because I set y equal to 0. And so now I can find the velocity at the end. I know 2 kilograms, 10 meters per second. I fall at height of 4 meters. I know the mass, I know g. So I solve for the final velocity, and the final velocity is about 13.3 meters per second, just faster than the 10 meters per second it had at the top. It gained that extra velocity by losing potential energy. That amount of potential energy all went into kinetic energy, which made the total speed now greater. And finally, you can get the exact same result if you do it using the work energy theorem. Because I know the net work is the only thing doing work on the object is a component of the gravitational force. And the work done by the gravitational force, you could either say is mg sine 30 times the length of the incline, or it's just the straight down distance because it's independent of path. The easiest way is to say the work done by gravity equals mgh, or mgy, I should have said, if I'm using the same variable, which is exactly equal to the loss in potential energy. Okay? And so that amount of potential energy goes into changing the velocity of the object. And so basically I have a certain amount of kinetic energy. This amount of potential energy is going to go into increasing this by that same amount. And so we can get the exact same final velocity equation as we had above. So this may all seem a little bit confusing, but I wanted to lay it out there. I want you to think about what I've just been talking about so that try to make as much sense of it as you can, because once we really start using this and we do some examples, it's really, really easy to use and it starts to make really clean sense. You know, it's basically just taking something from pile A and putting it into pile B. It really, really is. So think about this, try and get a sense of the idea of how the work energy theorem I can use to find my change in kinetic energy with multiple forces, or if I'm having conservative forces, I can recast the idea of its work done by the conservative force as a stored or potential energy of that that force is able to store inside the field, if you will, the gravitational field. That's a lot of terminology. Don't let me confuse you too much. A little rough around the edges, but I want you to jot down any questions you have and try and make the best sense of this as you can. And once we start working with it, I think you will find it not to be too bad. In fact, I think you'll find it to be really quite useful. Okay, so that's it. I am now going to sign off as soon as I go back to my. Now, at the end of these things is always like this. I can't figure out how to turn it off. Here we go. QuickTime Player, file, new screen recording, and I stop it.